Hi, and welcome to the SFPE webinar on how to prevent thermal runaway in lithium-ion batteries. This is Louis Garazzi, SFPE's Director of Professional Development, and I'll be moderating today's webinar. Before we get started, I'm going to go over some information in regard to the webinar logistics. First, all participants will receive a certificate of attendance for 1 PDH. To receive a certificate, you must stay online for the entire webinar. Certificates will be sent out via email in about 1 week. Also, we do not provide copies of the speaker's PowerPoint presentation. However, we will be posting a video of this presentation on SFPE's YouTube channel and website within the week. Additionally, you can ask our speaker questions by writing it in the webinar dashboard. You may ask a question at any time. However, we will not be taking any questions until the end of the webinar. Today's presenter is William Sudah. William is a mechanical engineer and lives in South Florida, currently working for Xtralis. He has over 14 years of experience in gas detection and works with engineers in the design of gas detection and layout, as well as sequence of operation. William is also a principal member of NFPA 88A and has been invited on numerous occasions to present with fire marshals on safety and design requirements, and continues to offer his support to this date. So with that being said, welcome, William.
Thank you all for being here today. Today we're going to be talking about thermal runaway in lithium-ion batteries. Lithium-ion batteries, as you know, they're widely used today, but unfortunately, occasionally they do go into thermal runaway. And today we need to learn how these batteries fail, what are these stages of failure, and how we can stop it and prevent thermal runaway in order to mitigate the risk. So I'm going to go ahead and start. So the presentation today might be oriented towards energy storages and data centers and advanced detection design in order to try and prevent thermal runaway. However, it can be applied into any application where you have lithium-ion batteries. Just to give you a little bit of an introduction, lithium is the second element in the periodic table. It does have great advantages. It's known to charge a lot faster compared to many other elements. It does have, it does last longer than other technologies. The cycle count, in terms of cycle count, think of it this way: when you charge your device from 0 to 100%, this is considered one cycle, or from 50 to 100%, half a cycle. So lithium-ion batteries do have very long cycle count, and as a result, they can last us for many years before we have to replace the battery, or the battery starts losing its efficiency. And then it does have a much higher power density, which means it can hold more charges than any other technologies out there. And as a result, you can have your device lasting you an entire day or many hours before you have to charge it again. And it's also considered to be the lightest of all metals, which means we can have portable devices and move with it at ease. Lithium-ion batteries, however, do have some limitations. And as a society, we have built some safety net around this technology because of the limitations that the technology has. Some of these limitations, the battery itself, or lithium itself, is known to be very fragile. We have to protect the battery itself from a deep discharge. On our devices, once the percentage reaches 0%, the device will shut down. The reason why it's shutting down, it still does have some power into it, maybe about 20% remaining, but the operating system is letting you see that it's actually 0%, so you have to shut it down and charge it. That's because if we let lithium-ion batteries go into a deep discharge, meaning a real 0%, we will not be able to charge the lithium ions anymore. And think of it this way: the lithium ions are swimming in a liquid, and they're widely dispersed in that liquid. Once it goes into a deep discharge, all of these lithium-ion atoms are accumulated at the bottom of the battery, and then they will not be swimming in that liquid anymore. So we have to protect that. We also have to protect the battery itself from overcharging. This is because a lithium-ion battery will continuously keep on taking energy, even if it's full. So then we program the operating system once it's at 100% to shut down the charging. This is why we all go to bed at night. Once we plug in our phones, we go comfortably. The phone is not going to explode because the operating system will just simply stop that. Short circuit does happen. We're going to be talking about that. They are also temperature sensitive, so we need to also protect these batteries from hot temperatures. Aging is also a concern, and we're going to be talking about that. This is because some dendrites or whiskers will start forming inside the battery itself. We're going to talk about that. And finally, the industry is not fully mature. The reason why the industry is not fully mature because we have different lithium-ion battery manufacturer, and they all have their own secret recipe when it comes to the liquid electrolyte, which is inside the battery itself. So just to explain the battery, you have the positive side, you have the negative side, and you have a separator in between. And the electrolyte is actually a liquid, a combustible liquid. And that liquid is in charge of carrying these lithium ion atoms from one side to another, depending on if you're charging or discharging. So without this liquid, we will not be able to transfer the charge. And this liquid is what manufacturers are always improving on, and they have their own recipes. So the understanding why batteries fail is very important. What we call in this industry, first, you must have an abuse factor. That abuse factor can be anything, can be a collision, a crush, penetration. So once you have this penetration, you're actually penetrating the separator. The separator is what's keeping the positive side away from the negative side. If they touch each other, you're going to have an explosion or a short circuit, and then it will explode. So in a collision or penetration, you will actually have, destroy the separator, and in the process, the battery will explode. But there are other abuse factors as well. Overcharging is one of them. Overcharging will create a chemical reaction. We're going to be talking about that. And then battery misuse or abuse. And then being exposed to high temperatures as well. And of course, manufacturing defects and the short circuits caused by dendrites or whiskers. So once the abuse factor is allowed to continue, the battery then will go into thermal runaway. And once the battery is into thermal runaway, you will have propagation, and then of course you will have explosions and fire. So let's dig in and understand precisely how a lithium-ion battery fails. Now, this liquid is in liquid form, or electrolyte. I like to call it liquid to simplify it. So this is a liquid that is inside the battery. That liquid will start transforming from a liquid state into a gaseous state. So once inside the battery, and this only happens when there's an abuse factor. When there is an abuse factor, that liquid starts becoming into a gas. This gas will start building up inside the battery, as you can see in this picture here. As the pressure is building up, the temperature is also rising. Now the batteries, they have a safe vent on top of the battery. So as the pressure is building up, it's going to push the vent out, and the solvents, which used to be a liquid, now is into a gaseous state, will just rush outside the battery, and it's being vented to release that pressure. The problem occurs at that stage. You still don't have any failure. The battery is failing, but it's still safe. At that point, the separator is still intact, and the battery is dealing with that internal pressure on its own. The problem occurs as you have more and more liquid turning into a gaseous state. The more pressure you have on the inside, the more the temperature is rising. And when the rate of pressure or heat generation is much greater than how much it can be vented, at that time the separator will start melting, degrading, and by that time the positive will touch the negative and the battery will explode. So you really think about it, the failure of lithium-ion batteries is that liquid turning into a gaseous state. And once the pressure builds inside, it will be released through the vent. However, as more and more liquid turning into a gas, the venting is not fast enough. Then the internal heat is going to rise. It's going to melt the separator, and it will explode. Now, there are two reasons or two causes that can cause the electrolyte to turn into a gas, from liquid into a gas. Overcharging is one of them. Overcharging is simply an extra current on the anode itself. So the anode will have extra current, and because the liquid is touching the anode, what's going to end up happening is a chemical reaction, and that chemical reaction is going to start transforming that liquid into a gas. So at that point, there's no heat. This is just simply a chemical reaction. But then you have overheating. Overheating, you can think about it, that's a different source, overheating a battery other than overcharging. So overheating, will think of it as it will cook that liquid, and it will start boiling and turning into a gas. So two reasons, or two causes that can turn the electrolyte into a gas: overcharging and overheating. And then the separator will melt, and there you have it. The whiskers, or what we spoke about earlier, the dendrites, these will occur as the battery is aging. Now, a university professor about 6 or 7 months ago determined that ethylene carbonate, which is one of the chemicals used in the electrolyte, and not by all manufacturers, by some, is the cause of making dendrites or whiskers grow inside the battery. And once they grow and they reach the separator, they will penetrate the separator, and now you will have a short circuit. This is why probably changing these batteries every 4 or 5 years is a good idea, just in case within their secret recipe they have ethylene carbonate being used. Now, that study was not verified yet by other scientists, so there is a lot of discussion on this topic as well. So we all remember the sad event that took place in April of 2019 at the Arizona Public Service facility in Surprise. This was a very sad incident, and I believe, and our thoughts, our prayer goes out to the fire marshals that are still injured and have not been back to work until today. What happened here was a thermal runaway. And then the batteries started releasing a lot of chemicals, including some LEL levels. And when they opened the door, thermal runaway was still in progress, but as it saw more oxygen within the space, it just exploded. So we're going to be referring to some of the things that we did within NFPA 855 in order to try and prevent something like this again. And then, of course, we've had several fires in South Korea. You can simply go on Google and just type South Korean energy storage fires and hit the image button, and then you will see a lot of images of what happened. And there's also a video that I'm also going to be showing. And then, of course, we're all consumers and we have our own devices. We've seen on the news many devices that caught fire due to battery defects. Okay, but let's understand the battery failure stages. The very first stage we discussed was the battery abuse. The battery abuse could be thermal, which is heat, overheating, or electrical, which is overcharging, and of course you have the mechanical abuse. During that stage, this is when the liquid inside the battery starts changing the state from being a liquid into a gas. At that time, the pressure is building up inside the battery. The battery is going to off gas, and this stage, which is your second stage, what the Korean call the golden time. They call it the golden time because this is the stage that you can stop thermal runaway from occurring. At that stage, once you detect these off gases in the air, you can immediately shut down the charging station or the battery rack and prevent it from going into thermal runaway. If you keep the abuse factor going on at that time, as I explained before, the separator inside the battery itself is going to start degrading and it's going to start melting. At that time, the battery is releasing all sort of chemicals and gases into the air, and you will get some smoke with it. Unfortunately, by that time, um, uh, failure is imminent. By the time you get to the smoke level, that means there's already a degradation inside the battery itself. And that chemical reaction becomes an exothermic reaction. Exothermic reaction, self-contained, and it even generates its own oxygen, which means it's almost impossible to stop that. The battery itself has to burn itself out. So this is the golden stage, which is the off gases, because by that time it did not start that exothermic reaction, which means we can stop the battery from going into thermal runaway. By the time you get to smoke, it will get to fire immediately. So as a preventative action, of course, nowadays we have early detection required in many data centers and many different applications. Early detection of smoke is extremely important because you could have different factors or causes that can cause a fire. It could be a hot wire that will eventually turn into a fire. So it is imperative that we still monitor for smoke. But when it comes to energy storages or maybe data centers, or any other application where you have lithium ion battery storage of some sort, we need to monitor off gases. And the off gas monitor can then send a signal, shut down the equipment, and prevent the battery from going into thermal runaway. So if you remember, we spoke earlier and we said that the industry is still premature. The reason why it's still premature because every factory, every battery manufacturer has their own recipe of the electrolyte or the liquid inside the battery itself. They keep on enhancing those chemicals in order to make your battery charge much quicker and in order to make it discharge much slower. So they're experimenting on what type of chemicals they add inside these batteries. As a result, when they off gas, they will be off gassing different chemicals altogether. Some batteries might release a large percentage of CO2 other than the other gases. Some other batteries will release a combination of hydrogen, carbon monoxide, CO2, and of course some solvents. So it is not ideal for us to start monitoring every gas depending on who the gas manufacturer is. So it would be much more better for us to actually monitor the combination or the cocktail of these electrolytes. So this way we would have one type of sensor that can just monitor the electrolyte gas or the solvents in the air and shut down the battery itself. So it must be able to detect the blend of all these gases. So today we have a standard for mandating energy storages, which is the NFPA 855. There's still a lot of work that NFPA 855 that needs to be done with NFPA 855 due to the APS event that happened in Arizona. Now it's a standard to have LEL detectors inside the energy storages, or it's a standard that authority having jurisdictions can follow or not. However, keep in mind, and you will see some experiments done here, the LEL levels were added just to protect firefighters in case they have to open the doors of the energy storage or maybe a data center, and now they have to worry about the safety of the firefighters. So just in case LEL levels were very high in that room, they needed some sort of protection, and having these LEL detectors in place was important is important for it to prevent the Arizona fires again from happening again. But does that prevent thermal runaway? The answer is no, because these gases are released in huge quantities only after a battery went into thermal runaway. So what we're trying to prevent by having LEL sensors is to prevent another explosion when you open the door so you don't hurt any firefighter. But it will not stop thermal runaway from occurring. To stop that, we need off-gas monitoring, and I believe they're still working on that. At the same time, we have UL 9540A. UL 9540A is a test method that will evaluate and study how a particular battery would fail. So no battery manufacturer can sell any lithium ion battery without first doing the UL 9540A testing. They're not allowed to sell these batteries before they do UL 9540A testing. So UL 9540A is not a passing type test that you're supposed to pass or not supposed to fail. No, this test will only understand the characteristics. They will study the type of battery being used. They will study how the battery fails on the cell level, and they will overheat the battery. They will purposely make it go into thermal runaway, and then all these results are documented. And on a module level as well, it will be tested, and even on a rack level, as well as inside the entire container. And this can also be applied for data centers. So UL 9540A will document the performance criteria of these batteries so we can better mitigate how we can deal with that risk. So during the testing, we will be able to deal and understand at what temperatures and at what time or how long it takes until the off-gas event happens for that particular battery. And of course, they will document at what temperatures on average the thermal runaway will occur for that type of battery. Now, if there are authorities having jurisdictions on this call, this is very important for you guys to know that. You have the right to request these reports. Authority having jurisdictions, as well as fire department, as well as building owners and insurance companies have the right to contact UL 9540A and ask them. We have some batteries, lithium-ion batteries, that are being installed in our jurisdiction in our county, and the batteries are, for example, an LG type or a Panasonic type. Can you share with us the testing reports that were conducted on these batteries as well? And then the UL 9540A will share these reports so that you can look at it and see how long it took for the battery after the abuse factor to go into thermal runaway, as well how long it took for the battery to off gas. But I also encourage that you ask UL 9540A to ask them to also show you the reports and the study of the off-gas monitor. The off-gas, so the off-gas monitor was not used on every single testing, but it was used on enough testing, and UL 9540A do have the report of the off-gas monitor, and you can actually see when the off-gas monitor detected it, and there might have been also some experiments where who knows, that they were able to shut down the equipment prior to going into thermal runaway. And if not, you will still see how long the off-gas monitor predicted that failure before it occurred. So these testings are very important, and of course, authority having jurisdictions can have the results of these testings. So this was a test done on an off-gas monitor being used by a third party. There were other detectors in the space as well, and this testing was due to an overcharge. Now, I just want to explain a few things first. The battery management system is designed in such a way to be able to predict these failures. Just so that we're clear. The battery management system is just like your operating system on your devices. It is designed to predict any temperature changes. It is designed to predict any voltage fluctuations. The problems that has been occurring because the battery management system has not been able to always identify the problems. And that is simply because there are so many variables when it comes to detecting thermal runaway using the battery management system. That doesn't mean the system is not going to become better over time. It's just that there are many variables. A fuse inside the battery is supposed to shut down the minute the battery has enough current in it. That in some instances might not be able to shut down because of battery manufacturing defect. the temperature is not being measured across each battery. It's being measured maybe 2 sensors per module. And as a result, you're not truly taking the temperature into consideration or for each battery type. And of course, fluctuations in the battery not being detected by their system. So there are many different variables, which is why we believe we need to have a separate system monitoring and preventing thermal runaway just in case the first system by the manufacturer would fail. So in this experiment, an overcharge released these gases. And then you can see the off-gas monitor detected. Here is, these temperatures are normal, 50 degrees Celsius and 45 degrees Celsius. That's about 113 Fahrenheit. When you charge your phone and you try and touch your phone or your laptop, you'll see that the battery is getting very hot at that time, and it's probably close to this temperature. So that is not an indication. When you have an overcharge, it is not, and you cannot have an indication with the temperature, because as you can see, the off-gas monitor here prevented the thermal runaway at a lower temperature. Okay. So overcharging is the chemical reaction, and that chemical reaction does not at first necessarily increase the battery temperature on the inside. So you can see here how it was detected. Another test here that was conducted as well is increasing the cell at 5 degrees Celsius per minute. And purposely, they were increasing the temperature at that for that cell. So after 25 minutes, you can see the off-gas monitor detected some off-gas, and they kept the experiment going on. They did not stop any equipment from charging or discharging simply because they wanted to see how long the off-gas monitor would take to respond. So the experiment was allowed to continue. After 11.6 minutes, the battery went into thermal runaway. And as you can see, only then smoke was detected, because by that time you started having the meltdown inside the battery, and of course the battery started generating its own smoke and fire. So that early warning in this example was 11.6 minutes. In another example, you can see this was a little bit shorter, so you got on average maybe 6 minutes here. And in this example, this time they connected the off-gas monitor to a disconnect switch, and immediately, the minute the off-gas monitor saw the off-gas, it shut down the equipment and it never went into thermal runaway. So as you can see, and in here we kept it going, and it did still go into thermal runaway. Now I want to explain the different types of batteries. Now you have the cylindrical type, and you also have the pouch type. The pouch type is what you have in your cell phone, in your computer devices, and it's also being used in some energy storages, depending on who the supplier. Now, the cylindrical type is built to have a vent on top of the battery. So the vent will help us predict the off-gassing even earlier. The pouch type, unfortunately, we have to wait until there's enough gas inside the battery itself, and then the seal all around the pouch itself will break, and eventually the off-gas is released. So in these experiments, when you saw 4 minutes and 6 minutes, that was because it was the pouch type battery. But even with the pouch, we were able to prevent thermal runaway. So then from an industry point of view, what we need to work on with the battery manufacturers is to design a weaker spot within the pouch itself, so that we can also get an earlier warning when it's the pouch type, and not wait until we force until the seal is broken and allow the off gas to escape. So this way we can get an earlier warning. But despite that, thermal runaway was avoided, including when using pouch type. So in this example, carbon monoxide was one of the gases released, including methane and ethane and ethylene. And it depends on the battery manufacturer. You can see these levels started releasing very early on, and they were extremely low levels. But you can see a spike happened after the thermal runaway line, and that spike is methane. So one can assume that this battery type was the one perhaps used in APS. So due to some non-disclosure agreements, we can't reveal who the manufacturer is here, but this is just an example how different batteries operate and release different off gases. In this example here, the off gas that was released from a different type of battery is hydrogen chloride, hydrogen fluoride, and hydrogen. And as you can see, the LEL detector that did not even go off, which means even after thermal runaway, there was no LEL in this space. There was LEL in this space, and as you can see, so when the firefighters opened up the container doors, there was a high percentage of methane, and of course thermal runaway was still underway. So when it saw more oxygen and there's a lot of methane in the air, immediately it exploded. So those LEL detectors now being suggested or with NFPA 855 will only protect you right at that stage, because only here you start getting LEL levels rising, only after the thermal runaway. But what we're talking here is being able to detect the off gases way before any of these events will occur, which means you need to put a stop to it and not let it get to a level where you need to start planning how you mitigate the risk of fire and so on. It's good to have a secondary plan in case a system fail, but it should not be the primary plan. We're supposed to plan to prevent failure and not let failure occurs. So here's an example. The audio in this example might not be loud enough. So what I want to do is just point, in this experiment, we're heating up a battery cell. And after we heat the battery, the liquid will start transforming into a gas. The pressure is going to build up inside. And as the pressure builds inside, the vent is going to open. And when the vent opens, you're going to see a sparkle being released from this side and a pop. You might not be able to hear the pop, but you will definitely see the pop with some sparkle in the air. So I'm going to play the video now. So you probably saw some vibration if you did not hear this well. Look again in this area, you're going to see some vibration and you will see some sparkle. This is the electrolyte, the gaseous form of the liquid coming into the air. And at that time, there has been no degradation yet inside the battery. You are at the off stage, at the off gas stage, which is the very early stage, which prevents thermal runaway if detected at that level. So let's see it again. So I hope you were able to see it. Another video here. In this video, this is from the South Korean energy storage explosions. You can see at that stage you have smoke, and by the time you get to smoke, it's already an exothermic reaction inside the battery, and it's self-generating, and it's just have to burn itself out. And we're going to see this right now. So it's going to go from smoke to fire. So just to speed up the video here, and this is the after result. This is what happened in the energy storage in South Korea. That's because of thermal runaway. And we want to be able to avoid that, and specifically in data centers as well, because we have a lot of data centers nationwide. We have some high-rise buildings with data centers, and we want to be able to put a preventative method to prevent thermal runaway from occurring. And it's happening. So there are a lot of things that are happening. Authority having jurisdictions now are some of them in some jurisdictions. The ones that are aware of this now, they are demanding to have an off-gas monitor. So the more we learn about this and the more we understand how batteries fail, the better that we're gonna react and be able to prevent thermal runaway. So here's the fire, and I just want you to think, inside this box, there's only one cell one cell, just like the example, the very first video I showed you. And I want to show you how much energy this one cell has. And that's the end of your thermal runaway, one cell. And of course, if you have different cells next to one another, like we always do in each module, then you're going to have propagation. And now you have thermal runaway due to heat and overheating. And then you're going to have a continuous reaction until all the batteries fail. So how can we prevent thermal runaway? Well, we all know lithium-ion batteries are fantastic, but we need to be able to prevent it from going into thermal runaway. We can't depend on luck that let's just hope there are no manufacturing defects, because if we do, we're playing Russian roulette in a way. So we need to be able to plant a solution or an indicator that there is a problem. And to do this, we need an off-gas monitor. The off-gas monitor has been tested. It's been tested with UL 9540A, and there are some data on it, which authority having jurisdiction or an end user can demand and see what were the data on the off-gas monitor and how soon did it predict the failure for this type of battery. So that's one. So once you have your off-gas monitor, the off-gas monitor will then notify the fire panel through the controller, and then the fire panel can shut down power or can send a signal, or it can, the controller itself can be connected directly to the building management system or to a disconnect switch and cut power and then send notification at the same time. And that's how we prevent it. So you could actually do it at the rack level, or you could do it for the entire room, but then you will still know precisely where it came from. So for those of you that might be new to energy storage, just in a nutshell, we gather the energy from the wind and the solar panels, and we store it inside batteries. And the utility companies, and these batteries mostly are in containers, but sometimes you could have an energy storage in a building as well. So once you have the batteries inside the container and they're fully charged, the utility company will be able to switch the grid between fossil fuel and renewable energy. So there are 33 states that are going to be 100% energy dependent by 2050. 33 states. And these 33 states are today are planning and executing a lot of energy storage into their own states. And they are stored in this method. So they want to be 100% dependent and not having to switch between fossil fuel and energy. And that's why by 2050, instead of switching the grid from fossil fuel to batteries, you're going to go from battery zone A to a battery zone B to a battery zone D, and so on, or C. So and that's the objective. Now inside each storage, there are what we call the battery racks or verticals. So here is one example, and this could very much apply for a data center. So the design of how you would have your off monitor will honestly depend on the air inside the pod itself. So you can have the air converging all the way to the center. So the air is being forced from this side of the rack all the way to the center, like some developers are designing now. So the air is converging from rack 30 to the center and rack 14 to the center. And in this case, you would only need one monitoring sensor. So this way you could save on your costs. Or you could do what we recommend, which is one per rack. The reason why we recommend one per rack, unless we understand the airflow, is simply because sometimes they change the airflow on you. Sometimes the air is coming from one direction and then they change the design, or during the time of the day, and then they would force the air to come from the other direction. So in a way, if it changes the airflow, all of this has to be taken into consideration when we're doing the actual design. Now, you probably noticed that there are what we call here reference sensors. These reference sensors are the exact same sensor technology, the exact identical sensor as your monitoring sensor. The reason why we need reference sensors is to be able to avoid false positives. Now, if you remember, these electrolytes that are inside the battery, the liquid, is chemicals and solvents. These solvents can also be found in cleaning agents. So someone can come inside to do any cleaning, and the smell coming from the detergent itself might set off the actual sensor by the rack. So in order to avoid any false positive, you would have some reference sensors in place. The controller has certain logic built into it that can distinguish the signals and where it's coming from. And the logic built within the controller itself, it will be able to determine whether rack number 14 triggered due to an outside agent other than the battery itself or not. So, so in this example, you would have 30 monitoring sensors, and you would have 6 reference sensors and 2 controllers. So the best way to monitor for the off gases is to take the air into consideration. Now keep in mind, the sensor is very sensitive, and it will also be able to detect any off gases in a static environment. By static environment, I mean in a zone where there is no air movements. It is sensitive, and it will be able to detect it. However, when you have a mobile environment, or when you have air being forced from one side to another, you want to have your detector on top facing down, and eventually that gas is just going to circle back up and be detected. Another example is when the air is coming from the top to the bottom, you want your sensor facing on its side, because you want to be able to avoid any dust particle flowing in the direction of the gravity, and this way you'll be able to prevent any dust particles accumulating inside the sensor. Even though the sensor in this example is a 40 mesh, and it will prevent any dust particles from going inside. Now in this example, you have air coming from the front to the back, and you want your sensor facing down. Now in this example, the air is coming from the bottom to the top. It's okay to have your sensor facing down, and of course it can be outside the rack itself, so it doesn't have to be inside. And it would be facing down, and we're not concerned about any dust particles, because the 40 micron metal mesh will prevent any of those dust particles going in, and of course it's going against gravity anyways. So in review, and we're going to open it to questions, there are a lot of things that we still need to do when it comes to lithium-ion batteries. And we need everybody when it comes to authority having jurisdictions, when it comes to many people that are actively involved in the industry, to also help in making us a better society and be prepared to prevent these sad events from occurring. This is just a matter of statistics. When you build, when you have a data center with millions of batteries, it's just a matter of statistics. It will eventually happen. And what can we do as a society to prevent it? NFPA 855 is a great standard, but it does move slow, and we understand why. And then after the standard is out, we have to wait another 2 to 3 years. So then do we wait 2-3 years until we start mandating off-gas detection, or do we act now? And this way we prevent any more accidents from happening. So authority having jurisdiction will always be in control. Just remember the limitations. Lithium-ion batteries are great. Nowadays, we can't live without them. They do have limits, and we did set the right warning in order to avoid any accidents like this, but it's still not enough. So we need to go a step further. So understanding the 4 stages of failure is extremely important. The abuse factor, and we need to shut it down immediately after we get to the off-gas stage. By that time, it's not too late. And if we let it go a little bit further, then smoke and fire happens, and then we have other ways to mitigate that risk. So this is just a quick summary of what we went through, and now I am open to questions. And I have here Rick Reynolds with Ore Protection with me, and Paul Hayes with American Fire Technologies that will also be assisting me with any questions that you guys might have.
Great. Thanks, William. Yeah, we do have some time to take some questions, and we'd also like to just introduce and thank Paul Hayes and Rick Reynolds for joining us for the Q&A portion. So let's get started with the first question. Our first question is, you said the battery will explode if the separator is punctured. Clarification is being looked for in regard to, is that an explosion outright, or does it begin with a thermal runaway, which will then lead to an explosion from the flammable gases?
It will it will immediately explode. So the initial stages, it's just like I put the 4 stages. It will go into the off gas mode, but as it's allowed to continue, the internal pressure is rising on the inside, so there is no explosion yet. But the minute the meltdown happens, and as soon as the positive touches the negative, that's how your explosion occurs.
Great. Next question we have is how is the off gas generation discovered in that golden stage?
So very good question. So the off gas that we're talking about is a line tamer detector. I had to bring that up to explain how it was discovered. So the U.S. Navy had a very bad incident that took place back in 2007. They had a spy submarine that was operated on lithium ion battery. And one day they were charging the lithium ion battery outside the spy submarine. And when it caught explosion, when it went into thermal runaway, it exploded. And that scared the Navy. So then they had a government project to try and understand how lithium ion batteries fail. So Line Tamer won that project, and they started studying how lithium ion batteries fail. So after 2 years, they went back to the government and they said, this is how lithium ion batteries fail, which is a lot of the theory I discussed today. So then our government said, okay, how can we prevent that? How can we get a warning and maybe be able to prevent that? So then they came up with the off-gas monitor, and today it's being used on Navy ships, and that's when the government said, okay, now you can go and commercialize it. So that's how the golden stage was discovered, is through that study, and then multiple experiments were done to show that and prove that. There are even independent studies that are online that people can refer to or come to us, and we'll share these studies with you.
Great. So kind of playing off the topic of the golden time, other than stopping the charge to prevent continued abuse, are there any actions that could be taken for any internal or mechanical damage to prevent thermal runaway?
Well, once I'm going to probably ask Rick or Paul to jump in, but typically once you get the off gas, you shut down the charging station or the entire pod or maybe the entire data center, but then the system will also tell you where it came from precisely. So then you would be able to change the equipment. I think it's a general practice. You just want to change the batteries and not dig into what the problem is. But I will have Rick and Paul see if they, Rick, are you there?
Yes, I'm here, William. Thank you. I'll agree with you 100%, William. Once we actually find once the actual off-gas event took place and Lion Tamer had detected it, at that particular time, you're actually shunt tripping the pod or shunt tripping the battery string, and at that particular time, you prevented the off-gas or you prevented the runaway. So the next recommendation is to remove that string from the actual environment. So, Paul, would you agree with that?
Yeah, effectively that battery has now been damaged and it needs to be taken offline. The problem with batteries is once they've been damaged, you don't know when the actual failure mode can happen. But stopping it at that point is the ideal solution, and then going in and replacing it out, because we do see failure modes that can extend out for days, if not longer. So it does need to be replaced.
Yeah, there's another thing I need to mention, during the presentation I did not touch on that, which is the actual levels or the readings, and this might be in the questions. The detector is acting as an on or off, meaning is there a gas, an off gas in the air or not, yes or no. It does not give you an LEL reading, and it also does not give you a parts per million reading, unlike the conventional method of gas detection. And there's a very simple fact to that. In the conventional gas detection, we are allowed to breathe some of these toxics or LEL, have some LEL in the air without having any adverse effect on your health, or maybe getting it to a level where you're going to have explosion. So as a result, you have normal situations like in lead acid type batteries. Lead acid type batteries, it's normal to release hydrogen when you're charging and discharging. It's part of the normal cycle of lead acid type, but not lithium ion batteries. So in a hydrogen setting, we need to see those levels, because if they're too high, we need them to trigger an alarm. And if it's too high, then it's bad for your health if you're breathing that. First alarm level is an alarm level where you can breathe any toxic air for 8 hours a day or 40 hours a week. So we need the measurement. But when it comes to lithium ion batteries, it is not standard to release any off gas. These batteries are built to be 100% and completely sealed. So the minute any off gas is released, that means there's something wrong. We need to shut it down. So for that reason, we do not give you a ppm or an LEL. There's just simply no point. Whether you got 0.5 LEL or 1 or 0.01 LEL, you need to shut down the equipment. And there is no purpose for us to see what those levels are at.
Great, thanks. The next question we have is, if there is a manufacturing defect, is it possible to stop the battery from running away?
That's a good question. This will always depend on the manufacturing defect. So since we cannot be inside the battery and know what type of defect the battery is experiencing, it's really tough to say. But I can tell you, if the characteristics and the stages are taking shape in the same order that we displayed to you, then the answer is yes. But if the manufacturing defect is just going to be a sudden break down in the battery components that does not necessarily change the liquid into a gas, I'm not really familiar to talk to that point. So the answer is yes and no. There's just no way to know. But if the manufacturing defect is going to cause the liquid to start becoming into a gas, then the answer is yes.
Great. Could you comment on, oh, sorry, is there a follow-up here?
Yeah, well, I was just going to add a little bit to that. I mean, a lot of the defects are in the manufacturing process where contaminants are introduced, and over time those contaminants will break down. So it's really hard to stop that end of it from an abuse condition. And I've heard numbers from anywhere from 1 to 6 million to 1 in 20 million is the failure rate. And some of these facilities that they're installing out there are going to have that many batteries in it. So it's kind of like finding Waldo, which one is defective.
Great. So the next question here is, in the case of dendrite formation, in the case of dendrite formation leading to the separator puncture, will that produce off gas that can be detected in advance?
To my knowledge, this will be an immediate explosion, which is why I personally, if I have any lithium and I used to lithium ion batteries, I never let it go beyond 4 years, and I would just recycle it and get a brand new one. Rick, I don't know if you guys have any knowledge on this, Rick, Paul?
I do not on the dendrite evaluation. Paul, how about you?
Just, I think what you had said earlier, William, that once that dendrite forms, you complete the circuit, and there's not much you can do at that point in time.
That's precisely it. Thank you.
Next question we have is, what is the detection threshold and what gas species are being measured?
Yeah, we did answer that, I believe, didn't I? When it comes to this detector is an on or off, meaning is there an off gas in the air? Yes, then shut it down. Why? Because there is no purpose of measuring the actual quantity of that gas. Unlike the conventional applications we deal with, we need to monitor the levels because there are certain levels that are okay for us to keep things operating normally. And then once they get to a critical stage, then we start an exhaust fan or a strobe and horn. In this case, there is no norms. Once you see an off gas, immediately you have to shut it down. There's no purpose for us to measure the quantity of that off gas. So for that reason, there's just no measurement. I hope I understood the question correctly.
Yeah, I believe you did. The next question we have here is there any significant weight change that's happening while the electrolyte changes to gas that could potentially be used as a precursor to off-gas stage?
Did you say weight?
Yeah.
On weight on the cell itself?
Yes.
I'm not sure. So did anyone else understand that question? So you're asking if turning from liquid into a gaseous state, if this will change the actual weight of the cell itself. Presumably, since it's venting, the answer is yes. Rick, Paul, do you guys have any comments on that?
I've never heard that question, so it's an interesting question. I don't have a good answer for that, but I'm assuming.
Okay, so what's
once you start off gassing.
Yeah, once you start off gassing, obviously the weight is going to become less. What's the other part of the question?
If that change, if there would be a noticeable change in weight that could be used as a precursor to the thermal runaway.
I would say not. It's such a small venting.
Yeah, the weight, it's kind of hard to measure. I don't think they're looking to see if the actual weight of the cell has changed or not. Keep in mind, the manufacturers also want to make it more economical. In the past, they used to have a temperature sensor across each cell. Now they just have one per module or two on each side. So it's not really getting the actual temperature of each cell. It's actually happening for the collective cells together. Again, it's not as efficient as it needs to be, but they have their ways of determining the actual temperature. So I doubt anyone is going to add any measuring scale to see if the weight has changed or not.
Yeah, William, think that a rack probably weighs a ton or more. So to pick up that loss of weight of an off gas of a single cell is like throwing bricks in the ocean.
Right. Next question.
Yep. After off gases are released, are there any fire suppression methods that could help prevent thermal runaway outside of cutting power?
Rick and Paul, that question is for you.
Well, thermal runaway is internal to a cell. Propagation is from cell to cell. So once internal to a cell, there's nothing you can do. It's going to progress through thermal runaway. What we're hoping and working in the industry is coming up with methods that would limit the propagation from cell to cell, either through suppression, physical barriers, other methodologies that the industry is working on right now.
Rick?
So,
yeah, and I think I agree with Paul 100%. And I think the industry 855 is very scriptive in full-scale testing. And before a true solution, the script is very, very specific in validating the full-scale testing with whatever solution is actually going to be provided. It's just validating through a full-scale testing and making sure that whatever solution is actually put forth is to assure that that solution has been totally prepared. But it's the propagation and the continuation that we're very concerned about.
Louis, I know you have more questions, and that's fine. I just want to show a very quick video that shows how a thermal runaway occurred in this example. There was an off-gas monitor inside this vertical, and we purposely made it go into a thermal runaway. And during the off-gas stage, the minute the off-gas detector detects the off-gas, this timer will start counting, and this way you would see how long it would take prior to thermal runaway. So now the timer started, which means the off-gas monitor just detected the off-gas, and now we're speeding the clock, and you will see once it gets to the 11 something minutes. So that's how long it detected the off-gas. Go ahead with the next question.
Sure. So we're at the top of the hour. This is going to be the last question we're going to get to today. We have quite a number of questions left. We actually ran into an issue where we had an influx of registrants today, and we actually capped out our maximum number of attendees for this webinar. So congratulations to William and the group for having a great and appealing presentation to our membership. But the last question we'll get to today will be, can this detection be used in automotive applications? And if so, are you aware of any interest to use this technology there?
All right, so the answer is yes, it can. Now, whether it's being used or being considered, we can't discuss any. Just keep in mind, whoever we deal with, we are also bound by a non-disclosure agreement, which means nobody wants to tell you that it's being used. So I can't answer that question.
Okay, great.
And
well,
just a comment, Louis, just one comment. I would like to receive the remaining questions, please. If somehow you can, these questions can be sent to us via email, would love to answer all of them. I do have my contacts information right here. Just use your cell phone, take a quick picture, and see if you can also send your questions to me directly. I would love to answer them all.
Absolutely. Yep. Following this webinar, we will get you all of the questions and ask that you just respond to them at your convenience. We'll also be posting this video onto our website within the week. Due to the large number of attendees and participants and a few people who are unable to get in today, we'll probably look to get that expedited and up in the next 24 hours. So with that, I just want to thank everyone who participated in today's webinar, and thank you again to William, Rick, and Paul for participating in it and fielding these questions. So thank you.
Thank you all.